Hello, everybody. Welcome to our next lecture on hypothesis testing. And what I'm going to do today, which is a follow on really from what I did in the last lecture, is to present a couple of hypothesis tests that are potentially common in a lot of business applications, excuse me, certainly in a lot of government applications. And I'm going to show you a very simple spreadsheet tool with which to operate this. So many of you have asked, should I use a calculator or online calculator? You certainly may, but in the examples that we're going to provide, you really probably need a spreadsheet to do much of this work. And so I'll just do a couple very quickly today and show you some best practices of data analysis that I've developed over the years. So what I wanted to ask is, here's a good question, is the here's a good hypothesis, has Americans' consumption of gasoline and other energy goods gone up or gone down? So this is 2017 to 2018. And these are in per capita personal consumption expenditures on gasoline and other energy goods. So I've downloaded these from one of the websites which I showed you in our first data lecture. The Bureau of Economic Analysis Regional Economic Information System, which shows a wide variety of place-based economic statistics. And so these are 2 years, 2017 and 2018. You can see the average of the United States, went up from 947 to $1,069 on these two items, and so that's a signal, right? That's the mean at the national level. So we're really maybe going to be interested in, though, at that point level, it's obvious that Americans spent more, but there are a lot of questions. And one of them, which we can dispense away with right now, is inflation. We'll talk about that when we get to the economics section, but we're not going to talk about what the inflation effects over 2017 and 2018. We'll mention them when I do the statistical analysis. So there are a number of things we could do. We could have individual data on this. They're available from some of the base files of the Consumer Expenditure Survey, or just look at state and Washington, D.C. data. So I've downloaded these two. I've cleaned them up a little bit by eliminating here the regional values that are aggregated to the 12 broad census regions. And first thing we always want to do with data, the absolute first thing you want to do is graph it. And it doesn't matter if it's 10 or 15 observations or a million. And the reason is graphing of data allows you to visually inspect outliers. And if you these outliers could be caused for a variety of reasons, not the least of which might be simple coding errors. And so, less so in the federal data that has gone through several layers of review, but oftentimes if you're getting a data set from a big data source at your business, or if you're using some commercial third party source, very common that an error of a decimal point, for example, will occur. And a lot of historical data sets are the same way. So you've got to be very cautious about this when conducting your analysis. And those outliers may be very important, but you've got to know what they are. So we begin with, let's do a scatter plot just to see if there's any obvious data here that won't work, right? I want to select data across these two observations. So I've got 50 states and the District of Columbia, and we'll see what the scatter plot looks like. Wow, that's a pretty strong correlation here. We could clean up this graph. It'd be interesting. We could plot it. We'll talk about that later on. Plot a trend line on it. But you can see there's a very strong correlation between spending in one year and spending in the other year. And so that's really, and let's see who this big outlier is. Let's see who's spending the most on energy, right, in 2018. Um, North Dakota. Wow. North Dakota and Wyoming. They're spending a lot on energy. Interesting. Cold places might be playing a role. They're also both energy exporting states, and so they may be less inclined to save in those areas. Interesting, but what we really care about is, did Americans spend more or less in subsequent years? So let's set that chart out of the way and take a quick look. And to do this, we want to go to data analysis. I'm going to go into our data and data analysis. This is the tool pack that you've added. And what we wish to do is to do a t-test. And we're going to look and we're going to assume in this case that there are equal variances. We have a choice as a paired two sample for means. We have a two sample assuming equal variances and a two sample assuming unequal variances. And again, the difference here is that the signal to noise ratio is calculated a little bit differently if we don't know the variances, or if we know the variances or assume that the variances are equal or unequal. And since these are drawn from the same sample in 2 consecutive years, we're going to assume that they're equal variances. And then we'll take a look at what happens when we do both. So that's what we're going to do. Now, very simply, the first variable range here is going to be this. Right? I want to make sure I don't get the year in there. The software doesn't know that 2017 is a year and not a dollar spending. We'll pick the second one, right? And I'm omitting the national average there. Of course, we don't really want to add that. That's just a repeated sample. And let's pick an output range, someplace where we can read it up here, and click OK. So this gives us our information. So we have the mean of variable 1, right? And note that that's interesting. That's in 2017. That's different than the mean of the United States. And that's because we took the unweighted averages. So we weighted Vermont and Delaware, two very small states, the same as we did Texas and California. And so that's the first of our potential problems here, but we're not worried about that right now. And then the second one is this level, right? So this sample, again, these averages drawn from the average of all Americans. This is the average of all the states average. So an average of average would be different. And so what we have here is a t-test, right? There's the first t-statistic. That's a 1.76. Remember when I said we're kind of looking for 2 as an average? This is the critical value here. Let me explain that. So what that means is that observing this sample, we believe that if we were drawing random samples from this population, that better than 20 out of 100 times, if we were to draw 100 samples, only fewer than 5 of those would be incorrect or outside of within the confidence interval. So generally, the hypothesis here that we're looking at would be that these are that have the same mean, and this rejects the hypothesis. What this says is that the the first year, the first sample 1, which is 2017, is less than, that's why you have a negative t-statistic, than the average, or than the variable 2. And so, and then we could have done it the other way around. If we flipped it, we would have got exactly the same t-statistic, but it would have a positive value, right? And so that just would say that variable 2 was higher than variable 2, and a t-statistic would be 1.76 instead of a negative 1.76. Now, so in doing this, we assumed a two-tailed test. So we didn't impose any expectations that 2017 would be higher or lower. If we had if we were to decide to do that by looking at the mean data, and we had a one-tailed test, this would be the t-statistic, right? 1.66, and the critical value about 0.18. And remember, I said that the original student's t-test had values that were 0.01. That's at the 1% level. Confidence that these means are different. Oops, sorry, I can't do that. You have a 0.05, and that is the right, and then 0.10, which is the 10% level. And so these are the common, if you talk to a statistician, these are the levels of statistical significance, the 1%, the 5%, and the 10%. And so in both instances, whether we assume a two-tailed test or a one-tailed test, these would meet this broadest level. And again, disciplines are different. More empirical disciplines that, like say economics, and political science, for example, are going to be less worried about the statistical significance than they are the coefficient value, how much the difference actually is. Um, I'd say a more mature statistical value would actually treat both the size of the effect and the signal to noise ratio and the signal to noise ratio as being important in this. And so in this sort of test, what we find is that we can confidently say that in either a with equal variance or unequal variance or an equal variance that we have differences in these two. Now let's do a second test. Let's do another data analysis, and we'll assume unequal variances at this time, right? And see how this plays out in our actual analysis. So we'll here again is the first sample. Here is the second sample. We'll put the output range here proximal to the first one so we can make a visual comparison, and we'll pop that out and we'll see what happened. Okay. So in this case, the D statistic is exactly the same, and that's because the variances are probably very similar. And I'm obviously missing a step. Right, because we could do I could have done a variance test, but in the variance test, we're going to get different numbers. There's no way we're not going to get different numbers, right? So in this case, the variance was that size and the variance was that size, but if they're equal variances, they're going to give, in this case, out what, 7 decimal points are giving precisely the same answer. Well, not for the two-tailed test, but they're very close. So I think we have a lot of confidence that, and this is called a robustness test. If we do the first and we use this assumption and then we test it using a different assumption, we're getting the same answers. We have more confidence or robust, instead of using the word confidence in statistics, we think that the answer is more robust. And that's really the way that we approach these problems, is not to be confident or happy with our, I don't like the word confidence because that has unique statistical importance, but we develop a more robust belief in the quality of our analysis when we do several things. So here we've done a visual observation, we've done a two-sample t-test assuming equal variances, one with unequal variances. We're getting effectively the same answer. So if you were doing quality control of a product, and instead of this being state per capita personal consumption, you'd be finding important information from this work, and you would be able to go to your boss and say, look, I have a lot of belief that these two samples are different, and that could either generate whatever production change or marketing change or that you think is important. Let's go off to use another example here. So this is now 2 years. I'm going to look at per capita personal consumption on healthcare, and this is in dollars, right? So you can see there's been a big increase in this case. And so let's do exactly the same thing. Let's start by inserting a scatter plot diagram, and we'll select the data here in 2 different samples, right? And we'll see what it looks like. And so we've plotted these. A lot of correlation here, a high degree of correlation, obviously, between one variable and the other, but not perfect. And I'll be showing you more how we do these. This is scatter plot is really a linear regression, and we'll show you here in the next class how that works. But that gives you a sense of the the variability of the data. Because you always got to be uncomfortable a little bit that there's a problem here. So let's go to our data and data analysis tool. All right, let's do the equal variance assumption again in a two-tailed sample. Right, and the reason I picked 2010 was because that was the year the Affordable Care Act was passed. 2018 is the most recent data we have in per capita expenditures. So let's pick these samples first. There's 2010, 50 states in the District of Columbia. Let's do 2018. And let's pick an output range that we can visually observe. That one probably would have been fine, that sort of stock value. And there we go. And so, wow, now we have a t-statistic of -8, right, which is about 4 times 2. So the critical value is that value. So let's put that into a number value, right? Right, so that's much more than 0.01. So there's a lot of confidence that this is not a random outcome. And so the point of the confidence, the probability value, is the confidence that you have as a researcher that the results that you've developed from this sample across 2 different sets of data is not random, that it hasn't occurred by accident. And so here I've used all the U.S. states, and in every instance, healthcare spending rose over this time period, some by more than others. But what we worry about in statistical analysis is that we're drawing on population. We're drawing a sample from a population. In this case, we have a population, so we treat it much the same, but we're concerned that the observations that we have maybe don't provide a clear answer because there's a lot of noise in the data. So let's say we were to go out and instead of sampling per capita personal consumption expenditures, at the average to the state level, let's say we went out and just drew a sample of 300 persons. And we looked at their personal per capita spending on healthcare. And then we would draw another sample of 300 persons. And then draw another sample of 300 persons. What we're concerned with are those 300 people representative of the average person in America. I mean, there's 330 million of us. And so if we drew from a state with low spending like Alabama, or a state that had high spending like, let's say Hawaii or Massachusetts, we might not have a nationally representative sample. Or if we were to draw from a population that was had a lot more disease, if we were to pick in a place, randomly draw, somebody with who was facing a very expensive cancer diagnosis that year, that mean would certainly throw the entire sample into out of whack, because you could easily have somebody spending $1 million in healthcare spending, and of course it's not out of their own pocket, it's out of healthcare savings or it's out of insurance, but $1 million annual expenditure for cancer treatment or for a transplant surgery is not uncommon at all. And so you can see how that would throw off the sample. Or if you had a whole bunch of 22-year-old men in the sample who may spend nothing on healthcare expenditures in a year, those are things that would be, I think, highly problematic. Now, in the sampling that we do in healthcare, that's clouded by insurance, which is designed to smooth those irregularities over a lifetime. So for most Americans, the biggest healthcare expenditure they make in a year isn't the out-of-pocket expenditure, it's the insurance spending, which is spent by other people in a typical year. Nonetheless, you can see how something that has a lot of variability, you'd be concerned that a sample might be misrepresentative. And so a t-test would tell you that if the sample was misrepresentative. if you, and particularly if you had several samples, whether one of them was problematic. And then the other use that you might have is you may want to look at different groups. You may want to see, is health spending by people in Alabama really different than people in Arizona? So you'd want a big sample of Arizonans and a big sample Alabamians to make that comparison. Or you might say, oh, I'm really interested in men spending less than women on healthcare. So you could draw a long sample of spending on on healthcare by women than by men to see if there's a statistical significant difference. Or are African Americans spending less than white Americans on healthcare? So those are be interesting research questions in which potentially a T statistic would, just comparing means, would give you some information. And the t-test is useful because it is the most commonly deployed signal to noise ratio yet devised. So a guy, I just go back to this, a guy working in a Guinness lab doing quality control long about 1905 came upon this idea that has swept through science and is used in, in nearly every discipline that relies on numeric computations from a sample. Whether or not you're an electrical engineer doing sampled observations of telecommunications through space, or if you're a sociologist studying, the propensity of the types of diapers that families wear, you're going to use T statistics to help divine the signal to noise ratio in the data that you're using to explain the phenomenon that you're trying to understand better. So that's kind of a powerful tool, but you can see from the examples that we have on gas and energy, or particularly in healthcare, why just comparing two means may not be sufficient. That really what we care about in most research is controlled variation. So wouldn't it be interesting if we could take two observations here in these data and control for other variables? So instead of drawing a sample of people, let's say draw a sample of African Americans and draw a sample of white Americans and draw a sample of women and draw a sample of men and draw a sample of Hispanics and Native Americans, or draw a sample of people with bachelor's degree and without bachelor's degrees, which would all be interesting questions about healthcare spending. What if, what if we could devise a way where you could draw one really big sample and then account for all of those variations without having to do individual means tests across these? What if we could, as researchers, control, we want to see if healthcare spending is different between groups, and we could control for sex and gender and education and age from a single sample. That would be a far more interesting series of hypothesis tests. We're getting to a much more complex approach to science other than comparing two means. And that is really what the remainder of the statistics class will be on. And what we've done today is simply provide you a couple of contexts to do either a one or two tail t-test. I've showed you the process of plotting data. I've given you an example of where you could get data. And those are sort of the way that we're going to do the testing of this. I'm going to give you opportunity to make these calculations on your own from data that you can draw from your own and send to me. And at the end of the day, those will be important tools for you to take forward into the class. But the future of research that you're going to confront in all the business disciplines, or if you move into any other social science or even engineering, is going to be linear regression, or using a t-statistic when there are more than one variable that you would care about measuring. And with that, we'll close out the t-statistic test, and I'll see you next week.